Okay, so soft actor critique is defined as a soft policy iteration process. So this is an extension of the policy iteration process that we've seen before. If you remember, in policy iteration, we started off with some policy, did policy evaluation, evaluated, for instance, the Q value for that policy. And based on these Q values, we came up with a new policy that is better than the previous one. And now we evaluate the new policy and continue this process iteratively until we converge on a policy. So in soft actor critique, they defined a soft policy. So these are slightly different Q values for a given policy, and not the hard Q values that we previously saw. What does it mean? So they define the Q values actually initially similarly to the previous, to the original Q value definition that we saw, which is the immediate reward. The Q value equals, for a state and action pair, equals the immediate reward that we see after taking the specific action in the specific state, plus the discounted state value of the expected next state, the expected state value of the next state. Right, and of course the next state comes from some distribution of next state based on your transition function. Now specifically, so this is similar to what we've seen before, this Q definition, but now they have a specific definition for the state value, which now takes into account the entropy of the policy in the next state. So we're trying to propagate actually higher Q values for actions that lead to states where we have random control, right? More of a random policy. If we have more of a random policy in the next state, then our Q value will be inflated, will be increased. Okay, so how was that defined? So as before, the state value for any state, specifically for the next state when we do this computation, is defined as the expected Q value from actions drawn from our current policy, plus the entropy temperature times the entropy term. So here, this is exactly the entropy term for our policy. Why is that? You might remember that we defined the entropy as the summation over all possible outcomes of the integral, depending if you're in a continuous case or discrete case, of all possible, the probability of seeing the specific outcome times the log probability of that outcome. However, we saw that instead of summing the probability times the log probability of them happening, we can use the definition of an expected value and simply state that as the expected value drawn from our distribution of the negative log probability. Right? This is exactly the same by definition of an expected value. And of course, usually we want to use the definition of an expected value instead of iterating all possible outcomes, because we're doing reinforcement learning. We're doing sampling, one sample at a time. So we can combine these two together, the expectation over the action drawn from the policy, and say that our state value in the next state, when we propagate Q value, equals some combination of the Q value and the entropy value. Okay, so again, higher entropies will result in higher Q values in the previous state. Okay, so in some sense, we'll encourage action that lead us to states where we act more randomly in, okay, towards acting more randomly. Doing this process over and over again, if we go through the entire state space and perform this policy evaluation, these updates over and over again, as long as we do infinite often visitation, we visit all states and action pairs, we are guaranteed to converge on the correct soft Q value. So this is a similar result to the results that we saw for actual Q values. By adding the entropy term, we are still not losing the guarantee of convergence. Of course, in most cases we won't we don't want to run until convergence and then update our policy. We probably do them, in soft actor critique we do them in the same time, but for the sake, for pedagogical senses, we'll start by differentiating between policy evaluation and policy iteration, and then we'll see how to combine them and do them both together at the same time. So next, let's see how we can do a policy improvement step. So now we did a policy evaluation. Let's say that we converged on specific Q values. Let's say we did the policy evaluation until convergence. Now we need to improve our policy and get to the next iteration, right? To get the next policy. So we'd like to update the policy towards, or what we do, in soft actor critique, is we update the policy toward the exponential of the old soft Q values, right? Why the exponential of the Q values?
Softmax.
Right, we're trying to match, so now we're trying to match a specific distribution, policy distribution. And this specific distribution is the one, it's a distribution that is defined over Q values, right? And we saw how to define a distribution over Q values with one good approach to do that would be a softmax function. And if we do so, again, it is guaranteed to result in an improved policy in terms of its soft values. Okay, so how do we train, or how do we get a new policy that is closer to the softmax policy based on the Q values? So we need some distance measure to close the distance between our current policy, or the policy that... So the policy that we're going to produce it uses an approximation, so we might not be able to get the exact policy, but we want a policy that is as close as possible to the softmax policy that is defined over the Q values. So in some sense we want to define a space where we would like to find the closest policy. So we saw such a, not a distance measure, but a way to approximate how to evaluate the similarity between two distributions, right? We saw that before. This is the KL divergence, and now, so what we're saying is we would like to find a policy that a new policy for the next iteration that minimizes the KL divergence between itself and the exponent of the Q values, the softmax values. Okay. That is, the desired new policy should be as similar as possible. As I said before, we might not be able to get an exact similar policy due to approximation limits, right? Imagine that we have a linear approximator as our policy, right? We won't be able to fit anything, but we would like the policy that minimizes the distance with our target policy, which is the softmax distribution over the Q values from the policy evaluation step of the previous policy. Okay? It's important to note that the partition function z pi old here, this is just used to normalize. It's used to normalize the distribution, right? The softmax distribution, but as you can see, it will be a similar value to all possible outcomes. So we'll see later on we won't actually need that. It does not contribute to the gradient. Once we'll do gradient steps, we can actually ignore this z value here. And now we define soft policy iteration. We have policy evaluation, as we saw before, soft policy evaluation, and then policy improvement over a soft policy improvement, right? Over the distributions, as we just saw. If we do each one of these steps separately and until convergence, then the entire process will probably converge to the optimal maximum entropy policy, depending on the alpha that we set. This is guaranteed to converge for the tabular case. Of course, once we add function approximation, things usually our guarantees are not applicable. Yes, question?
So in soft actor critic, they seem to be making a KL-based update, policy update, similar to PPO. Can you use the same? So if with the trust region guarantees apply here, if we use the same clipping technique used in PPO?
Ooh, to add, you could. That's very complicated. Okay, so we define the soft actor critic algorithm as a soft policy iteration algorithm, where we add a function approximator for both the Q function and the policy. Specifically, the Q function is a deep neural network with state features and action as input. Right? So a state and an action as input, and Q values as the output. And it has tunable parameters, which we'll use theta to represent the tunable parameters in the Q network. Our actor, the policy, is also a deep neural network with state features as input, and the output is a distribution. Specifically in the basic soft actor critique algorithm, they use a multivariate Gaussian to represent that distribution, right? Where the number of dimension for that Gaussian is the number of the action dimension, continuous action dimensions that we might have. And so the way we represent this multivariate Gaussian is the vector of means, one mean per dimension, and a covariance matrix for all action variables. Okay, once we output these values, these are parametric, this is a parametric distribution, we output the parameters of the distribution, and that defines the distribution. And it's important to know that once we have such a continuous distribution, this means, or it assumes that the action is defined by a set of continuous variables. So each action is a dimension that can take continuous values. Now you might ask yourself, okay, so how do I apply this in a discrete action setting? So you can always take a discrete action and have and set it as a continuous value of probabilities, right? For the specific discrete action that you're considering. Now in practice, instead of doing the policy iteration, instead of running evaluation and improvement to convergence, we optimize both networks with stochastic gradient descent simultaneously at each time step. So how do we update the soft critique? The soft Q function parameters are trained to minimize the squared loss of the soft Bellman residual. Okay, so this is something that we've seen before. Only now we use the same loss function as we did for regular Q updates. Only now we have a special definition for the state value in the next state. So instead of simply taking either the argmax of the actions or the action given by the current policy, we first of all consider that action, but also with the addition of the entropy term. Okay, so we define the gradients towards these soft Q values. And once we have this loss function that is defined as the squared error loss over the soft Q values, we can easily take the derivative of this loss function and of the gradient of this loss function, and we can perform stochastic gradient descent on samples from the environment. These updates make use of a target soft Q function with parameter theta bar. So this is something that we've seen previously, for instance, when we went over DQN, where we have two networks. So we're learning Q values, we have two Q networks. One is updated at each time step, and the other one is used for gaining the current Q values for bootstrapping, but we don't update it at every step, but in the original DQN algorithm, we update it every so often, every C steps. In this paper, instead of updating it every so often steps, they suggest using an exponential moving average to update the target values. That means, I'll show you the pseudocode in a second, but they update our target network at each step, only, let's say, some delayed update. I'll show you the exact equation in a second. And this, they claim this is shown to stabilize training compared to updating every several steps. By the way, you can use the same update rule for DQN. Should work the same. I think mostly it is done this way instead of the original way they proposed for DQN. So next, how do we train our soft actor? So the policy parameters can be learned by directly minimizing the expected KL divergence from the Q-based policy, right? We'll call it the Q-based policy is a softmax over our Q function. We'll call it pi prime, right? So we would like to reduce the KL divergence. This will be our loss function. So this is just the definition of the KL divergence, right, for two policies. It's the probability, so it's an integral over all actions, the probability of getting a specific action in a specific state, log times log the factor of probabilities of taking the specific action under the policy what we're trying to minimize, and the target policy, the pi prime. Okay, this is just the definition of a KL divergence between two policies. Now we would like to find the policy parameters, in this case it will be theta, as I defined earlier, for our target policy, which minimizes the KL divergence, right? We would like to minimize that. Now, interestingly, you can see that we have some expression that looks like an expected value, right? We have an integral over a probability of some outcomes times some value that depends on that probability. So instead, we can rewrite that as an expected value of log of just the value defined here, without this probability, right? So this is just the definition of an expected value. And indeed, this is what we're going to use, because we're doing sample-based updates. So what we would like to do is to minimize the KL divergence over all visited states, or equivalently over the expected state, right, from following a specific policy, or maybe from our replay buffer, and to minimize the log probabilities, the log's difference, factor of probabilities between the policy that we're trying to tune over the policy that we are targeting. So how do we perform the actor training? So again, we have the minimization term that we would like to achieve. We can further simplify that as log of the probability that we're trying to tune minus log of the target distribution that we're targeting, right? It's just breaking the log expression. It's just log rules, right? You can break it as follows. What is our target policy? Well, it's just the softmax over Q values, right? Defined here. The target policy is a softmax over the Q function, right here. And again, I can rewrite it as follows. I can rewrite the objective function as follows, but now using the policy that I'm targeting here. And as I said earlier, we can ignore the constant log partition function because it will not impact the argmin value. Okay, it's a constant. So we'll just remove that, the log of the z function. And what we're left is just the following. We'd like to minimize the expected state and the expected action of the log of the probability of taking that action under the policy that we're training, minus 1 over alpha times the Q value for that state and action pair. Of course, right, I just removed the log and the EVA and the exponent because, well, I can just cancel it, right? It's log of exponent. I can, at the end of the day, so I can multiply all of this expression by a constant, say alpha. It won't affect the argmin, and indeed this is what brings us eventually to the final equation that is used by soft actor critique. Okay, which is alpha times, we would like to minimize alpha times log the probability of taking a specific action in an expected state, minus the Q value of that state action pair. Okay, so how can we minimize the actor loss, which is highly non-convex, as you can see? Well, we can use stochastic gradient descent, as always, right? When we update our tunable parameters to be the same, minus some step size times the gradient of the loss function. So we assume that our policy outputs a distribution, for instance, a multivariate Gaussian in the original SEC algorithm. So specifically for a Gaussian, it outputs a mean vector and a covariance matrix, right? And we see this before. We know how to compute gradients of the loss function with respect to mean and sigma for a Gaussian. This is something that we've seen before, specifically at topic 14, when we discussed actor critique. I showed you the derivation for this. But other parametric distributions also have well-defined gradients. Soft actor critique specifically uses a multivariate Gaussians, the basic version of soft actor critique. And we already saw how to take the derivative of the mean and variance for a Gaussian. But as I said before, you can see papers out there that use other parametric distributions, which also have well-defined gradients. However, but there is a problem here. So now we define the soft actor critique algorithm, and if we just implement it and run it, it doesn't work very well. Why is that? Because the gradients tend to be very noisy because of the noisy sampling process. So we get some value here, some gradient value for a loss function, but that's very sensitive to the action that we're sampling from our policy here. Okay, and we want to somehow mitigate this instability. And indeed, this is suggested in the paper. We're mitigating this by using the reparameterization trick.